Hi everyone, let's take a look at question 5 in topic 8 problem set. This is a question about comparing the strength of lattice energies in ionic compounds. So remember that the term lattice energy is used to denote the strength of ionic bonds. So if we have two ions, cation and anion interacting with each other, which one is stronger? So to understand the strength of lattice energy, we have to look at the factors that matter in the attraction between two ions. And remember that that's all based on something called electrostatic interaction. And electrostatic interaction depends on two factors. One is the charge of the two ions that are interacting. So Q1 would be the charge of the cation, Q2 would be the anion. And then it's inversely proportional to the size of these ions. So the further away the ions are, then the weaker the interaction, the closer, the smaller the R is, the stronger the interaction. So in other words, when we're looking at the interaction, we have to always compare the charges and the ionic radii. Now, the other thing I want to point out is that the charges is always a more important factor compared to the radii. So I just want to show you this little table here, which shows the ionic radii of various ions. And you can see that the sizes between, say, a +1 and +2 cations that are right next to each other is not that different. So one of them is 100 and the other one is 70. It's not exactly half, but the charge of this is +2, the charge of that is +1. If you go, say, from sodium to all the way to cesium, you can see that sodium is 100, cesium is 160. So there is some difference there, but then it's not quite double. Whereas the charges a lot of times would double or triple or quadruple depending on what type of ion combinations that you're using. So if charges Q1, Q2 and size R point to opposite directions, so let's say in one case Q1, Q2 says that one compound is stronger and then the charges said the other compound is stronger, then Q1, Q2 is always more significant. So you would always pick the compound based on your charge comparison. Okay, now if the charges is exactly identical, then that's when you would choose the R or use the R as a way to determine which one is stronger. All right, hopefully that's enough of a background information. Let's take a look at our actual question. So the first one we have is LiF versus CSF. So let's take a look at charges first. So Li is a +1 cation, F is a -1 anion. Cesium is also +1, F is also -1. So in this case, you see that the charges are both identical, +1, -1. So there's no stronger one in this case, so we have to look at size. When we look at size, we notice that we have to compare the sizes of the cation and the anion. Well, the anions are both fluoride, so that means that relatively speaking, there's no difference between the two. That means the only thing that would give a difference would be the cation. So we have to compare the size of lithium ion to the size of cesium ion. Now, when I'm doing this, I don't necessarily need you to find out the value or the number that corresponds to the radii, but what you need to remember is just the trend. So the trend for these ionic radii is that you can see clearly pretty much in this picture that as you go from left to right, things get smaller, right? That's because you're in the same shell, same principal quantum number, same energy, but then the number of protons increase. And then if you go top to bottom, you can see that things get bigger. That's because the charges, relative charges remain about the same, but then the size increases, or the shell, number of shells increases. Okay, so that's the general trend. Left to right gets smaller, top to bottom gets bigger. And then remember, there's this thing called the Isoelectronic Series, and those are for things that have the same number of electrons. And so for the same number of electrons, then you need to compare the number of protons. So for example, if you have sodium versus magnesium, number of protons in this case is 11 for sodium and 12 for magnesium. Both of them have 10 electrons, so they're isoelectronic. Since magnesium has more protons, that means that the protons are better able to exert its attraction to the electrons. So then the size of the magnesium ion is going to be smaller, so sodium is going to be bigger. So just to look at the actual sizes here, you see that sodium in fact is 102, magnesium is 72. So indeed, that's correct. Okay, so we'll use that later as a way to compare the sizes. But again, no need to actually know the values. You just need to use the trends in order to make your prediction. So going back to our problem, we're trying to compare lithium ion to cesium ion. Well, cesium is way down in the periodic table. Lithium is way on the top here. So as a result, lithium is going to be smaller compared to cesium. Smaller means a stronger interaction because R here is inversely proportional to your lattice energy. So I would say in this case, the lattice energy of LIF is stronger than the lattice energy of CSF. Okay. Now, keep in mind that stronger means more negative, right? Because why is lattice energy a negative number? Because Q1 in this case is a positive value because it's a cation. Q2 it's a negative value because it's an anion. So when you multiply positive and negative, you get a negative number. Let's go to B now. B is NABR versus NAI. So let's first look at charges. +1, -1, +1, -1. So again, from a charge perspective, no difference. And then let's take a look at size. Well, sodium is the same in both compounds, so we're not going to care about that one. We'll just compare the size of bromide versus iodide. So looking at the periodic table, or if you remember that where these elements are located, bromine is higher compared to iodine, right? Bromine is right here, iodine is below it. So iodide then is going to be a larger ion compared to bromide. So from here, I would conclude that the lattice energy of NABR is stronger than the lattice energy of NAI. Let's take a look at the third one, BaCl2 versus BaO. Here we have a +2 for barium, -1. Now, even though you have 2Cl here, that gives you a -2 overall. Remember, the actual interaction in the lattice is between a +2 and a -1. And then you have, another +2, another -1. That's how the actual ions are packed together in the lattice. So what we're comparing is the strength of attraction between these two ions right here. So +2, -1. The barium here is +2. The oxide is -2. So in this case, there's a difference in the charges. On one side, where you get -2, the other side you get -4 when you multiply. So this is a stronger interaction. Okay, so I'll put a check mark there. And then let's look at sizes. So barium is the same for both, so that's not going to affect size. But chloride and oxide, we should compare those two. Well, chlorine is below oxygen in the periodic table, so it's going to be bigger. The oxide is smaller, that means that's also stronger. So we're going to pick this one as the stronger one. So you can see that both check marks tell us that the lattice energy of BaO is stronger than the lattice energy of BaCl2. Let's take a look at number 4, Na2SO4 CaSO4. Here we have a +1 for sodium. Sulfate comes as a unit, so that would be -2. Calcium is +2, sulfate is -2. So again, looking at this, we have a -4, we have -2. So this is a stronger one, just from charge. Let's take a look at sizes. Sulfate is the same in both compounds, so we're going to ignore that for comparison purposes, but let's compare sodium versus calcium. All right, well, sodium is above calcium, so it should be smaller, okay? So if sodium is smaller, that means that, of course, you would say that that would make this one a stronger interaction. But remember what I said earlier at the beginning, which is that when you have conflicting situations where the charges point you to one direction and then the size point you to the other direction, the charges would always win because the sizes typically will not differ by that much. So in this case, I would say that the lattice energy of calcium sulfate is going to be stronger than the lattice energy of sodium sulfate. Now, if you actually go back up to that table that I had earlier and compare the size of sodium ion versus calcium ion, you notice that sodium ion is 102 and calcium ion is actually 100. Calcium is actually slightly smaller, although for all intents and purposes, you can say that both of them are about the same size. Our prediction earlier was that sodium is going to be smaller, but this is why I said this radius is not that important, because sometimes you get conflicting situations that cause the size not to be as predicted. And so in this case, clearly, because of the charge, the calcium is going to be stronger compared to the sodium sulfate lattice energy. All right, let's take a look at 5, which is Kf and K2O. So we have a +1, -1 with Kf, and then +1 and -2. So here, this is going to be a stronger one, right? And then K is the same in both ions, so we're just going to, in both compounds, so we're going to compare just the radius of fluoride versus the radius of oxide. Well, these are isoelectronic ions, as it happens, because they both have 10 electrons, if you count it, but then one of them has 9 protons, the other one has 8 protons. So as I said earlier about isoelectronic series, the more protons you have, the smaller that's going to be, so then fluoride is going to be smaller. Now, if fluoride is smaller, that means that it's going to be a stronger lattice interaction, right? So you'll pick that one as your stronger one. But now you have those conflicting situation again between charge versus size, so you'll pick your charge as the winner. So in this case, lattice energy of K2O is stronger than lattice energy of Kf. Okay? And if you actually go ahead and compare the sizes of F- versus O2- minus. O2 minus F140, F minus is 133. So it's true in this case that F minus is smaller than O2 minus. However, the size difference is really minimal. In fact, they're almost the same in terms of size. So having a -2 in one of these guys versus a -1 in the other one, clearly the -2 would dominate a lot more. Okay. All right. Last question is Li2O versus Na2S. So this one we have a +1, -2. Na is +1, S is -2. So the charges are the same in terms of how the ions are. So that means we have no difference there. We have to look at the distance now. Let's take a look at the radii of the ions. So the radius of lithium ion versus the radius of sodium ion, and then the radius of oxide ion versus the radius of sulfide ion. Lithium is higher than sodium, so that's smaller. Oxygen is also higher comparison to sulfur. If you want to look at it in the periodic table right here, you see oxygen, sulfur. So as a result, that's also going to be smaller than sulfide. So both of them point to the fact that these two are smaller. Smaller means stronger, right? So therefore, the lattice energy of lithium oxide should be stronger than lattice energy of sodium sulfide. Okay?